All right. Good morning, folks. I hope you were able to watch the video yesterday and understand it okay. And hopefully, I was able to encourage you to explore this FET lab a little bit more to help you understand what we'll be talking about today and what we'll be talking about in terms of the gas laws. Okay. So please make use of it and allow it to help you. Okay. Just one quick note before we get started. Remember on Friday, we're going to be meeting live and Zoom. So the same Zoom information that we used yesterday. Please make sure you use it for Friday. We're going to meet together on Friday. We're going to review for the exam next week to finish out the semester. And then I'm going to take any questions you may have about the gas chapter, about chapter 13. We'll be done for the semester in terms of the material. Okay, so please make sure if you weren't able to make it yesterday, I know a few of you were not able to make it yesterday. Please show up on Friday. That way, then I can take your questions in regard to the exam. I'll go over how we'll take the exam. Remember, I had mentioned yesterday that I'm going to change the, we're not going to be using Edmodo. I'm going to use a different mode to administer the exam. So please make sure you show up and so I can explain that to you. It's not going to be too different from Edmodo. I don't want to change things up too much, but I think this new platform is going to allow us to get the exam done a little bit more smoothly. Okay, so please make sure you come by. Don't forget to show up for class on Friday. Okay, so we're going live on Friday, folks. Okay. All right. So with that said, then what I'd like to do then is I want to finish up with this general review of gases. Okay, and I want to focus today on pressure. In the first part of the class today, I want to talk about gas pressure. And so today, then we're going to be examining this part here, because if you notice with the gas laws, with two of the gas laws, it talks about how pressure can change. Okay, where the Avogadro's law we won't deal with, but I do want to mention that really quickly in terms of how it affects gas pressure. But I do want to talk about that. I want to talk about then what leads to gas pressure. Okay, so you can imagine that here is our barometer, or this is a manometer here. This is a gauge that measures pressure. We talked about how yesterday this gauge right now, before we put anything into this chamber here, reads zero. It's 0 atmospheres here, and so it'll read zero because it's a vacuum. What we have inside this chamber right now is a vacuum. Okay, and so if there are no particles, there's no pressure. Okay, we had also mentioned then that the temperature here reads zero. There's no temperature reading here as well, because you remember we talked about yesterday how the very first question I asked you, how it's the motion of the gas particles as they move around here that leads to the temperature as well. So the motion of the gas particles is a result of heat. It's kinetic energy, I'm sorry. That kinetic energy is directly related to heat energy, which is measured by this thermometer here, okay? All right, so with that said, then let's go ahead and take a look at what happens here. We're gonna go ahead, let's put in 50 particles. Okay, so there I have injected into this, into the chamber now 50 gas particles. What we're doing here, folks, is we're making the connection between the microscopic movement of these gas particles to the macroscopic observations we can make on this pressure gauge here and on this thermometer here. And so as you notice it, as soon as we put into the chamber here some gas particles, we get a reading on this pressure gauge right here. So the 50 particles, and again, make sure you understand this is not a direct correlation. We're not saying then that whenever you have 50 gas particles, you will have a atmospheric read or a pressure reading of 5.4. The idea here that is as soon as you put in gas particles, you get your reading here. Okay, so please don't make that assumption then that somehow 50 gas particles imparts a pressure of 6 atmospheres. Okay, all right. So with that said, then gas particles, as you put in gas particles, the pressure increases. So it's the number of gas particles right now that leads to the pressure. But let's imagine this: if the gas particles if they do not move, okay, if they do not move, then and they just settle down, you can imagine then that if there's no motion, then the temperature gauge go down. But if there's no motion, this pressure gauge would also read zero. The movement of these particles here, the movement of these particles is what contributes to this to the pressure here. It's not just the existence, not just the fact that these gas particles are in here, but what matters more is that you have gas particles in here, but they are in motion. Remember, the kinetic molecular theory stipulates then that these gas particles are in constant, random, rapid motion. As a result of this motion, if you notice here, they start colliding with one another. So it is not so much the presence of these gas particles themselves, and make sure we remember that from the chapter 13 material. It's not so much the presence of these gas particles themselves, but it's the gas particles as they move. As they move around, what they're doing is they are colliding with everything else around them. Okay, and so it's those collisions that occur. It's the collisions that occur that leads to the force that we talked about. Okay, they are pushing in on one another. They're not only pushing on one another. If you notice here, they are pushing in. They are bouncing off the walls of this container as well. And as they do so, as they bounce off the walls of these containers, that's what leads to the pressure. And so remember, these collisions then are perfectly elastic collisions, but it's the result of the gas particles here. And so let's go ahead and I'm going to pause it really quickly here. Okay, I'll pause it. Okay. And so if you take a look at this here, what we're going to notice then is it's the movement of these gas particles here. As these gas particles move in a particular direction, as they move in a particular direction, okay, they will interact, they will collide with one another. And if you notice then, as they move around, okay, in a random, rapid manner, they will bump into everything around them. It's these collisions. And for some of these here, it's the collisions with the walls of the container. Okay? As they move around, they bump into the walls of the container. As they push in, they apply a force. Remember, as they push in, they apply a force that we talked about. That force then is a result of their motion, obviously their mass, but also a result of the change in their motion. As they push in and they apply this force, as they do that, remember we talked about this also, they exert that pressure over a given area, and it's pressure over that the force over a given area that leads to gas pressure there. Okay? So as these particles move around and they push in, and if you can imagine this gas particle here pushing in on this part of the wall, and it's pushing in on that area of the wall right there, okay, then it exerts a pressure. But these particles have to be moving. So remember, acceleration here then is the change in the speed over time. Okay, so we talked about that as well. These particles will change their velocity. We talked about this velocity. They would change the velocity not because they speed up or slow down. The speed of these gas particles, remember, depends on the temperature down here. Depends on the heat energy, which is down here. Either we add or remove heat, but the change in velocity then will be a result of their changing in direction. So this one, this gas particle moves in and it bounces off in that direction. Okay. And as it changes its direction, it undergoes that acceleration. It undergoes this acceleration right here. Okay. And when that acceleration, when this particle has that acceleration, it exerts that force. That force then leads to the pressure that we see right here. And so that is what leads to the gas pressure. And that's what you want to make sure you keep in mind, folks, is that gas pressure is a result not so much of the particles being there, but the particles being there and the particles moving and changing their direction as a result of collisions. Okay? So it is the collisions, it's the collisions that these particles undergo. It's the collisions that these particles undergo that result in the gas pressure. So let's make sure we understand this. The gas particles have to be there, yes, but the gas particles have to be moving. They move, and when they collide, the collisions then forces the change in direction here that leads to an acceleration. So collisions here leads to that acceleration, okay? Because the change direction, so this is a result of a change in direction. The change of velocity is a result of the change in direction of those gas particles. And as those gas particles change their direction, they accelerate. That acceleration here leads to a force, that is a push that they have on everything around them. Okay? Push on the wall, push on each other. That push then, this force, leads to pressure. And that is what we see here that's being measured on this pressure gauge. Okay? So please make sure you keep that in mind as we go through this, because that is then the microscopic reading. That's how we're able to explain the pressure gauge right here. Okay? All right, so that's our gas pressure. So we now then have accounted for how that gas pressure is exerted. So again, make sure you keep that in mind as we go through this. That is something that you have to remember. And we can measure this gas pressure here. Let's go ahead and continue this. So we can measure this gas pressure here in the units of atmospheres. So you notice then that the units here are measured, gas pressure is measured in atmosphere. So right now the pressure inside the chamber is about 5.5 atmospheres, but there are different pressure units. Okay, so you want to make sure you keep this in mind as you move forward as well. So you notice here the two pressure units that are given to you are in atmospheres and kilopascals. Okay, so you have two pressure units there, atmospheres and kilopascals, and we saw then that the relationship between atmospheres and kilopascal is that for every 1 atmosphere you have then 101.3 kilopascals. You need to make sure you remember that pressure unit, this conversion factor here as well. And furthermore then, we saw that there's another pressure unit that's involved. And we saw then that 1 atmosphere is also equal to 760 millimeters of mercury. Now, millimeters of mercury is not used as much in science. Okay, it's more this one right here that you should remember, but make sure you keep that in mind as well. And so those are the conversion factors that we need in terms of dealing with the units. Okay, so make sure you keep that in mind as we move forward as well. Okay. All right, so with that said then, let's see what else. So we know how gas pressure is created. We know how these gas particles create pressure. Okay, then let's talk about then how we can change that gas pressure right here. Okay, how can we change this gas pressure here? Well, the first and the easiest way to take a look at this then is we add more gas particles. So let's go ahead and double the number of gas particles there. Okay, and so now understand this, there's not, you see then that the pressure then also increases almost by a factor of 2 as well. Okay, so the number of gas particles here increased. Let's go ahead and double that number to have 200. Now 200 particles here of gas particles in it. If you notice then that the pressure is increased. And so therefore we see a direct correlation. Let's go ahead and write this down. We see, and I pointed this out to you, we see a direct correlation between the number of particles, okay, and this is Avogadro's law right here, folks, number of particles and the gas pressure itself. So this is what we refer to as Avogadro's law. Okay. So this is Avogadro's law that states then the relationship between number of particles and the pressure itself. And we see then from this PhET lab here, as you increase the number of particles, you increase the number, you increase the pressure. Let's go ahead then and let's decrease. Let's go ahead and do the, let's do the opposite. Let's decrease the number of particles down to a half. And if you know, cut it in half, you notice then that the pressure goes down. So as you increase the number of particles, the pressure goes up. As you decrease the number of particles, the pressure goes down. So you see then a direct correlation between number of particles and pressure, and that is what's given to us in Avogadro's law. Okay, so that's what we see there as well. But do keep this in mind then, it's not so much the presence of those gas particles, it's more the collisions that occur. So if you have more gas particles, you can have more gas particles colliding with each other and colliding with the walls of this container. That is what leads to the increase in pressure, or the conversely, as you remove gas particles, you're decreasing the number of collisions, and so therefore you decrease the pressure. So remember, it's gas particles, it's the number of gas particles, but more importantly, it's the number of collisions that we have present as well. Okay, so as you do that, you'll recognize that. Okay, all right. Let's go ahead and let's take a look. So that's what we see there. Let's go ahead and let's, but I'm sorry, one last thing I want to point out to you then is if you notice then the temperature has not changed. Okay, so if you add in, it doesn't change as much as we see then with the, as the pressure there. Okay, so make sure you keep that in mind, that the movement of these gas particles then is what results in the change in temperature. Okay, so if we drop that all the way down, let's start all over. Okay, let's go ahead then. Let's take a look at another factor, okay, that affects gas pressure. Okay, so there we have then our gas particles in motion. We have our pressure here, and we have the temperature as well. Okay, all right. I'm going to go ahead then, and I'm going to add our. Hopefully you did this. This is our kind of our ruler here in the PhET lab. They had mentioned this as being a ruler, but actually it's just, it measures it for us. If you notice then, if you look down here, right now the width of this chamber is about 10 nanometers. 10 nanometer width. And so you can increase the width. And so if you notice there, as we pull out on this handle here, the width increases, or you can decrease the width by pulling it in, by pushing it in, and that decreases the width right here. So this isn't quite a ruler, but it measures it for us. Okay. All right. And hopefully you had a chance to do that. Essentially what we're supposed to do here in the PhET lab is by adjusting the width here, we are assuming then that there's going to be, we're going to correlate that directly to a change in volume, which it does. Volume is the measure of all three sides, length, width, and height of a three-dimensional shape. Okay? And so if you change one dimension, you obviously change the volume. Okay, so we're going to change the volume here by increasing or decreasing the width. Okay, so what we want to do then is we're going to see what happens to this pressure here as we change the volume, as we change the size of this chamber here, as we change the size of the container. Let's take a look at what happens to the pressure here. Okay, so as we decrease the chamber, as we decrease the volume of the chamber to about half, okay, what happens to the pressure here is that it increases. Okay? So as the volume decreases, the pressure increases. Let's go ahead and take a look at what happens as you pull out, and let's almost double it, and let's pull it all the way out to 12 here. As the volume increases, you notice then the pressure here drops. Okay? And so what we notice here is that the relationship, let's go ahead and write this down. We notice here then that the relationship between volume, so this is volume, and pressure is what we refer to as an inverse one. Why? And this is this is referred to as Boyle's law. Okay, so if Avogadro's law relates the number of particles to pressure, Boyle's law relates then the volume to the pressure. And if you notice, the way that we have it set up is different. Okay, here we have volume, here we have inverse pressure. Okay, and so what we're saying then is that there is an inverse relationship between pressure and volume, meaning then as we make the volume smaller, let's go ahead and do this again. As we make the volume, as the volume goes down, as the volume gets smaller, okay, so we see this, the pressure gets bigger. So as the volume goes down, the pressure goes up. So and we do the opposite, as we increase the volume, okay, that means as we make the volume bigger, the pressure gets smaller. And so that's what Boyle's law states. Boyle's law states the relationship between volume and pressure. Okay, and that was your first PhET lab that you had to do there. And so in your first PhET lab, we'll get to that in just a moment. Okay, we get the chance to see that occur as well. Okay, all right. Let's go ahead then, and let's continue on, and let's talk about the other gas laws that we have here, okay, the other relationships we have here. Okay, so let's go ahead. I'm going to reset everything really quickly. Okay, let's go ahead, reset everything. We are back. I'm going to go ahead and add in our volume measure here. Okay, and so number of particles here. And so again, I'm going to go ahead and push in the number of gas particles. There's a number of gas particles. The pressure goes up. Temperature here stays the same. Okay. All right, so we saw then the relationship between volume and pressure. Okay, let's take a look at then what happens when we change the temperature down here. Okay, so that was our third PhET, the second PhET lab that you had to do, which is involving the change of temperature here with the changing and how it affects pressure. Okay, so I'm not going to do anything to the volume here. I'm not going to change the size of it. I want to keep that constant. I don't want to change anything. You could have done this as well. You could have clicked that on. That would have held the volume constant. And if you notice here, and we'll talk about this in just a moment here, and I'll write this down for you. Okay. With each of these gas laws here, if you want to focus in on the relationship between whatever's on this side and pressure, okay, everything else has to be held constant. So that means then for this particular, when Avogadro's law, when we study that, we want to make sure then that volume and temperature are constant, meaning that we don't want those to change. Because if all of those factors change at one time, it becomes a little bit more difficult to predict the change in the pressure. That's where the ideal gas law comes into play, but we'll talk about the ideal gas law hopefully tomorrow. Okay, all right, and so or Thursday. Okay, and so with Boyle's law, then what has to be held constant then is number of particles, okay, which is not an option here, unfortunately. Number of particles, the temperature, okay, and number of particles and the temperature has to be held constant. Okay, so that way is then that they don't also affect the pressure as well. Okay, all right. So with that said, then with the when we talk about temperature, let's go ahead and talk about this. Okay, we want to make sure that the volume stays constant and the number of particles stay constant. I'll talk about that in just a moment. And so we can go down here to this gauge right here and change the temperature. And what are we doing when we change the temperature? We are changing the heat energy in here. So let's go ahead then and let's heat things up a little bit. Okay, so we're going to add heat energy. So what we're doing right now is we're adding heat energy. And as you notice, the temperature is going up right here. We see the temperature going up. It's reading now 544 Kelvin and 271 degrees Celsius. Make sure you can do that conversion as well. But if you notice, as the temperature goes up, the pressure goes up. Okay, and so the particles move faster. Okay, and as a result of that fast motion, you have more collisions, and because you have more collisions, then the pressure goes up. Let's go ahead and do the opposite. Okay, so let's go ahead and cool things down. Okay, well, that means then we are removing heat energy, and as we remove the heat energy, the temperature goes down right here, and as the temperature goes down, the pressure drops. Okay, and again, make sure you understand that we can relate what we can observe here on a macroscopic scale, temperature dropping, pressure dropping, with the motion of the particles. And that's the key idea behind this vent lab here, is being able to connect the motion of the particles on the microscopic scale with the temperature reading here and the pressure reading here on a macroscopic scale. Okay, so what we see here happening is that the particles slow down, but what happens? Why does that affect the pressure? If the particles slow down, they collide less. They're not moving as fast. There's not as many collisions that occur because they're not moving as fast, and so that's what that's what decreases the pressure. So again, it's the movement of the particles, yes, but it's the collisions that they undergo that lead to the pressure here. And so what happens then when you increase the temperature, as you add in more heat energy? Well, the particles move faster, and if you notice, you can do the collision counter here. I'm not going to do this for you, okay? This is an option for you, okay, that you can use to count the number of collisions. Okay, so play with that on your own. Okay, try with that on your own, but you can visually see that here. You can visually see then that there are more collisions here that occur, and that's what leads to the increase in pressure. So what can we say then is the relationship between the temperature here and the pressure? Well, let's go ahead and take a look at this. As we increase the temperature, or we decrease the temperature, the pressure increases or decreases in the same manner, okay? Which means then, in this case then, we've held the volume constant and also the number of particles. Okay, so number of particles and, number of particles and the volume has been held constant. That way then we get this. This is what we refer to, this is Gill-Sachs law. And that's what you were able to explore in your second PhET lab. Okay, so number of particles then affect the pressure. The volume then affects the pressure, and now we see then the temperature also affects the pressure, and all three of these relationships are stated in the three gas laws that we talked about here. Okay, and so what I want to do for us tomorrow then, okay, and we'll finish up with this. I want to talk about the fourth and final gas law. Okay. And then I want to hopefully do some problems with you, talk about what's called the combined gas law, and then hopefully we can start the ideal gas law tomorrow and then finish up with the ideal gas law on Thursday. Okay, so please make sure you get the homework done for set A done for tonight. Okay. What we'll do then is I'm going to hold off on assigning any of the gas law problems, but please start taking a look at section 14.2. Work through some of those problems. You had some practice problems from your PhET lab to do, and I think that was, I think, very doable for you. But try those, and I'm going to go through a few of those gas laws, and we're going to practice solving them. But I think you'll notice then, solving these gas laws are very simple. What I need you to do is understand what these gas laws mean, which is what we have right here. How do each one of these factors here affect the pressure? Okay. All right, very good, folks. So I will see you tomorrow. If you want to, come on by after school today. Get your questions answered, okay? And then if you want to, we can go through a few of these problems as well, okay? So if not, then I will see you folks tomorrow, okay? Have a good day, folks.